The topic I'm presenting is Anisotropic Multi-Component Topology Optimization for Additive Manufacturing with Build Orientation Design and Stress Constraint Interfaces. This is a joint research between Toyota and University of Michigan. Hello, I'm Yuqing Zhou from Toyota Research Institute of North America. Structural topology optimization has been primarily applied to design monolithic single-piece components. However, it is not difficult to quickly look around and realize that most structural products, from complex car bodies to simple chairs, are usually multi-component assemblies due to cost, ease of manufacturing, packaging, and other practical considerations. As for additive manufacturing, design for manufacturability has been investigated extensively recently, again, primarily in the component level. In our research, we are interested in design for additively manufactured assemblies. In a prior publication at JSICE, we have discussed the build volume and cavity-free constraints in a multi-component topology optimization framework. In this paper, we will introduce the build orientation design and component interface modeling in our multi-component topology optimization framework. It is widely acknowledged that additively manufactured components exhibit anisotropic mechanical behavior based on the chosen build direction. Transversely isotropic material model is often used to describe such anisotropic behavior where stiffness in the build direction is lower than the ones in other directions. In assembly design, component interface modeling is critical since joints can be a prime candidate for structural failure. In our multi-component topology optimization framework, the overall structural design and component partitioning are optimized simultaneously. An effective component interface model can help design the joint geometry and location for the optimal assembly level structural performance. Density and component membership design variables are used to design the base topology and component partitioning. Mk is the fractional membership of a design point to the kth component. While Mk is a continuous variable ranging between 0 and 1, the clear component partitioning at the end of optimization requires the membership to only one component being 1 and the rest being 0 at convergence. The build orientation design is parameterized with an orientation tensor method. In multi-component topology optimization, both the overall base topology and component partitioning evolve during optimization. The identification of component interfaces is especially challenging when the density and component membership design variables are still blurry, which is typically the case until very close to the end of optimization. After the boundary of each component is identified, as shown in the middle row, a component interface indicator I is proposed to identify component interfaces via a heaviside projection. Then, a maximum stress constraint can be applied only to the identified component interface region for the joint modeling. A user-specified joint stiffness tensor can also be applied to the identified component interface domain, which is different from base materials. The overall anisotropic multi-component topology optimization, considering component-wise build orientations subject to a volume fraction constraint and a maximum stress constraint at component interfaces, can be summarized in this slide. The objective is to minimize the assembly level structural compliance. Density, component membership, and build orientation of each component are design variables. G1 is the volume fraction constraint. G2 is the global maximum stress constraint at component interfaces based on a heaviside aggregation formulation. To compare the anisotropic multi-component design with the conventional isotropic single-piece design, a 2D cantilever example is presented in this slide. With 3 distinct build orientations, the resulting multi-component assembly has 4 individual components. The arrows on components indicate the optimized build orientations. The dark lines between the colored components indicate the thin layers of component interfaces. The optimized component-wise build orientations are mostly perpendicular to the major principal stress directions, which supports the empirical mechanics knowledge for maximizing the assembly level structural stiffness. The right figure presents the isotropic single-piece design with the same volume fraction. It is observed that the isotropic single-piece design has a different topology, which is comprised of larger number of thinner bars. To examine the effect of joint stiffness and joint strength on the optimized base topology and component partitioning, 2 examples are presented in this slide. In the left-hand example, 2 prescribed values of isotropic Young's modulus at joints are used. 2 designs have different base topologies and joint configurations. Due to the stiffer joint property, the design allocates the joint material at the loading location. The joint length is also notably longer to take advantage of the stiffer joint property. In the right-hand side example, for the case of unbounded maximum stress, joints appear at a high stress concentration location around the L bracket corner. On the other hand, with a stricter setting for the maximum allowable stress at component interfaces, the design avoids the formation of joints at high stress concentration regions. The assembly design that has a lower maximum stress at component interfaces is expected to be better guarded against joint failures and to function more reliably in real-world environment. To demonstrate the proposed method for more complex 3D structural design problems, a multi-load example is studied. 3 independent shear loads are applied while the opposite faces are fixed in all degrees of freedom. The resulting 3-component design has very complex geometry and component interfaces. It is a hollow structure with a fully closing outer shell formed by the 3 components. It is also noted that the 3 optimized components have almost identical geometries and build orientations, because the boundary conditions for 3 independent loading cases are rotationally symmetric. In summary, this paper presented a multi-component topology optimization method for additive manufacturing, considering build orientation design and component interface modeling. The base topology, component partitioning, and build orientation for each component are simultaneously optimized using a gradient-based method. The anisotropic mechanical behavior is modeled using a transversely isotropic material model whose less stiff direction is aligned with optimized build orientation. To model the stiffness and strength of component interfaces, a joint model is also proposed. Please also check our other recent multi-component topology optimization works if you are interested. Please feel free to reach out to us if you have any questions. Thanks for your attention.